All of that stuff that we did on the interior of the Earth should have been a review for you because we did the interior of the Earth already. We had talked about it at the beginning of the year when we did reference table page 14, right? So all that stuff should have been reviewed. So now we're going to move on to what happens, okay? What happens when things start to move, right? Underneath us, we have those plates. Now, guys, you need your reference tables on your desk for this entire, basically, unit, okay? So things underneath us are constantly moving. If you look at reference table page 5, right, that's all those plates, right? You have the divergent plate, you have the convergent plate, you have the, right, we're all looking at the reference tables, right? Now the arrows on those are going to tell me how the plate is moving, okay? If it's divergent, which way are the arrows moving? Away from each other. So that means the plates that are there are going to be separating, and that's where you're going to get the volcanoes coming up or the lava coming up and hardening and creating more of the crust. Right? What about convergent? What's happening? They go towards each other, right? Now, the convergent ones you can also have where one plate goes underneath the other, and the one that goes underneath the one, the subducting plate, subducting under, okay, is the one that's more dense. Okay? So just giving you guys a little bit of a refresher on this, right? Well, this is how earthquakes are going to form. Basically, when you have an earthquake, all right, you have a stress that's going to happen. Okay? And when that stress happens, all right, usually it happens at a weak point. All right? So you have this kinetic energy build up and build up and build up and build up until eventually it can no longer hold on to that energy. It needs to go somewhere. Okay? So you put a stress on the fault. When you put a stress on the fault, you get this buildup of energy. Right? You guys remember differential? Remember when we did differential weathering? Right? Differential weathering was just uneven weathering. So then differential stress is going to be uneven stress. Right? So it's not like you're doing a stress evenly across the board. This stress is happening in different spots at different times with different pressures. Okay? So they didn't figure out what caused it until the 1906 earthquake. Okay? Let's see. No problem. There was a 1906 earthquake that was pretty bad. It was one of the worst ones that they've seen. Or at least at the time. Okay? And this guy figured it out. H.F. Reed figured out what was happening. Okay? Basically, he said that the crust itself has these weak points. Okay? Those weak points are known as faults. Okay? Yes. I believe it was California. Okay? Now, those faults are naturally occurring. Those weak points naturally happen. Okay? Now, it's not something that was man-made. It just happens on its own. They're basically these cracks in the surface. Okay? And underneath those cracks, you have the convection cells that are happening. Right? Well, here's what it looks like, right? All you're going to see, guys, are cross-sections. All right? So the cross-section of this shows me that there's a natural fault line. Okay? It's like if you take a pencil right? We've all done it at some point, or you've seen it at some point. You take a pencil and you start to pull it. You start to push it a little bit, right? And you start to bend it. After a while, if you do it slow enough, you can actually see it build up. What happens eventually? What happens to the pencil eventually? It's going to snap, right? Because it's counteracting the stress that you're putting on it by bending it, right? So that's what happens over years. Now, we're not talking about like a year. We're talking about 100 years, okay? Over years, there's this buildup of stress, right? It wants to move, but it hasn't yet. It wants to move maybe like 1 centimeter a year, but it can't. It hasn't yet. So there's a buildup, a buildup, a buildup until eventually you actually have the whole thing move 100 centimeters in 1 second. Okay? So that's actually what happened. In the 1906 earthquake, okay, the energy underneath had built up so much that you can actually see the fence has moved. That fence here was connected at one point. It was one continuous fence. Then the 1906 earthquake happened, and it separated the fence. Okay? It moved that much in a couple of seconds. Yes.
What if your house was like in the south?
So if you're I don't want to say dumb enough to build a house on a fault line, but that's pretty much it, right? It's not a good idea because what you're doing is you're kind of you're testing nature by doing that. I did find out one of my former students is an engineer, and he told me that Alaska and California are the two hardest places to be an engineer. And the reason for it is earthquakes. Because in both Alaska and California, you're on a giant fault line. So when you're building buildings, when you're putting up buildings for houses, right, you have to make sure that the house can withstand a motion moving of an earthquake, and a pretty big one. Otherwise, it all topples down. And in Alaska, you have the weathering that you have to worry about. You have the frost wedging you have to worry about on top of it.
So, like, would you say, like, earthquakes, like, I want to say, like, how bad they are depends on how much the fault line is?
How bad they are depends on how much energy that they have built up over time. You know, and then aftershocks are a different story. Sure, yeah. Okay? So, the whole thing is that you want to be able to predict where an earthquake will be. Now, we are not on a fault line. I don't know if you guys remember a couple years ago when there was the earthquake that happened in Virginia, but we could feel it here. Yeah. It was kind of crazy. You didn't think anything of it. You felt like a bus was driving by or a truck was driving by. But it was an earthquake. All right, so you need someone to study these fault lines to predict an earthquake is about to happen, to make sure that we're prepared before an earthquake happens. Okay? So what seismology is it's the study of the kinetic energy. It's the study of the kinetic energy, okay, caused by earthquakes in waves. Okay, so it's the study of the kinetic energy caused by earthquakes in waves. So seismology is the actual field. So if you become a seismologist, you are the scientist who studies the kinetic energy that is caused by an earthquake, and we figure it out in waves. Okay? So, this picture here, if you have not already downloaded from Google Classroom, please do and put it into your notes. Okay? Because there's a bunch of vocab words here And again, this is a cross section. So we live up here where this green part is. This is the inside of the earth. Okay? Okay. So that black line is going to be the fault line. This here is the fault line, and you can see it on the surface of the earth as well. Okay? That's where the earthquake is going to happen. The focus is exactly where the earthquake happened. Notice that the focus is on the inside of the earth. Okay? It's the point where the earthquake happens inside of the earth. Okay? The seismic waves that come off, I call them like ripples, right? If you take a pebble and you drop it into water, right? Exactly where it hits the water is technically the focus, but the seismic waves would be the ripples that happen and come off of that. Okay? So those are the waves that come off or that are caused by that earthquake. Okay? Then right above the focus, because remember the focus is inside of the earth, the epicenter is directly above the focus on the earth's surface. Okay, the epicenter is directly above the focus on the earth's surface. Sure, the epicenter is directly above the focus on the earth's surface okay? And the epicenter is going to be where you have the most damage. Okay? That's where you're going to have the most amount of damage from the earthquake. Okay? Well, if you were a scientist, right, you need equipment to test this. Well, how do we know all this stuff? Well, because you have this thing that's known as a seismograph. It's the actual apparatus that tells me that you had an earthquake happen. Has anybody ever seen San Andreas or any sort of movie that includes an earthquake? There's usually that person. There's always a scene. I think it's hilarious, but there's always a scene where the person is sitting at the little seismic station, or like it looks like a little room. There's all kinds of cameras around, and then all of a sudden, I don't know why, every time I see a scene like that, it's a person who's not paying attention, they're drinking their coffee, they're eating a donut, their feet is up on the desk. Tell me what's wrong, right? It's every single time. They're not paying attention, and then all of a sudden you hear beeping noises, and they're like, oh my God, and the coffee goes flying, the donut goes flying, they fall off the chair usually, right? Because they notice on the seismograph movement. Okay? Woo-hoo. Go back. Okay? This is the seismograph. All right? It's literally a pen or a pencil on a rotating drum here. And what it does is it picks up those seismic waves. Okay? It picks up those seismic waves, telling me that somewhere around me there was an earthquake. Okay? So it picks up those waves and it tells me that somewhere around me there's an earthquake that's currently happening. Now, part of the seismologist's job is to figure out where the earthquake's focus is, or where the epicenter was. But how do they do that? Well, when we look at the paper itself, it looks like this. This is another one of the pictures you're going to want in your notes. If you do not have it from Google Classroom, you can draw it. Okay, so as the ground is moving, it generates those seismic waves. Those seismic waves are the P wave, the S wave, and the surface waves. Okay, so let's break it down. The P wave is going to get to that seismic station first. P stands for, what do you think, guys? Primary. Exactly. So the P wave gets to the seismic station first. Okay? It is a fast wave. It's smaller. You can see that it's smaller, right? And it's shorter. Okay? But that's going to be the first indication that somewhere around me an earthquake is happening. Because when the earthquake happens, it generates those waves. And like I said, it's just like a ripple. They generate out in every direction. And the way that you're going to know is that being at the seismic station, you're going to figure out which direction it came from. Okay? By figuring out how long these waves took to get to you. All right? The thing with P waves is they can go through solids, liquids, and gases. Okay? This is how we figured out what the inside of the earth looks like using these P and S waves. Because
Sorry, it goes through solids and liquids.
and yes, all three. Okay? This primary wave, okay, is one of the two indications of what the inside of the earth is made up of, or that we can infer it, because the primary wave went through all the layers. The S wave, what do you think the S stands for? Secondary, exactly. It comes second, right? Notice the difference between the P wave and the S wave. The S wave is more spread out, right? Its wavelength is bigger, right? It's longer, right? And the S wave is going to travel through solids. Okay? So when the P waves went through Earth's interior and the S waves didn't, we were like, oh, that's either made out of a liquid or a gas. Because P waves can go through solids, liquids, and gases, but S waves can only go through solids. So we had to figure, or we inferred, based on that observation, that parts of the Earth, depending on which section it was made up of a liquid. Question?
So you said S waves only go through solids, does that mean that, let's say a P wave is like going through gas, S waves goes through?
It would get stopped. Yeah. Okay, so lastly, surface waves. Surface waves are the slowest out of all three of the waves, which makes sense, which is why it's showing up last on this. Okay? And surface waves only exist near the epicenter. They only exist near the epicenter. So if you have surface waves that show up on your device, that means you're really close to the epicenter. Okay? And they pretty much go through all different types, solid, liquid, and gas. Okay? The surface waves are going to tell us what's happening at the epicenter. Okay? Now again, we can use these to determine where the epicenter is. Okay? By things like travel time, arrival time, origin time, and lag time. Okay, so normally I would do this in lab, but obviously you guys do not have lab and we're not really doing any more labs. So I need you guys to have your reference tables out, which I know you already do. But what we're going to do is we are going to not listen to this
PNH
guy.
photo helped change his life. Fred, tell us your story.
No, don't. Sorry, you can watch it on your own. Okay, so basically, you need to have your reference table out in order to do this. So your job, you guys did. Go ahead. You guys are all seismologists. Based on given information, it's going to be your job to figure out how far away the epicenter is. Okay? And here's how you do it.
Hi everyone, welcome to the Earth Science Regents Review podcast series created by the Honix Middle School Earth Science Department. Today we're going to be talking about page 11 in the reference table, P-wave and S-wave chart. Before we get started, there are some terms that you need to know. You have travel time, which is the vital times.
I love when things jump for no reason. Okay, so here's the vocab that you need.
Specific distance.
Okay? The first word, the first vocab is travel time. Okay? Travel time is going to be the amount of time it takes, the amount of time it takes P or S waves to travel a distance from the epicenter. So it's the amount of time it takes, the amount of time it takes P or S waves, P or S waves to travel a distance from the epicenter. Okay, so this is going to be in minutes and seconds. Okay, it's how many minutes and seconds did it take for it to go from the epicenter to the seismic station where you guys are all located. Okay, the next vocab word.
From the epicenter, you have your arrival time, which is the time that the P wave or S wave gets to you.
Okay, so the second one is arrival time. And this is going to be the actual time on the clock. Okay, it's the time in which the P or S wave gets to you at the seismic station. So it's the actual time on your clock when the P or S wave, gets to you at the seismic station. Okay? So it's the actual clock time. At what time does it show up at the seismic station? So when do you get that first P reading or that first S reading? Then you have
your seismic station. Your origin time is
your origin time. Okay, again, this is going to be a time on the clock when the earthquake started. Okay? It's the time on the clock when the earthquake started. Okay? So the arrival time and the origin time are going to be like 9:52 versus 9:59 a.m. Okay? So that's the arrival time, that's the origin time. The travel time is the amount of minutes in between. So if the origin time is 9:52 a.m. and the arrival time is 9:59 a.m., what is the travel time? It's just 7 minutes. Okay? Simple and easy. All right?
the time the earthquake starts. Lag time is different in arrival times.
Okay, so lag time,
Epicenter distance.
okay, lag time, LAG time, is the difference in arrival times for the waves. Lag time, LAG time, is the difference in arrival times between the waves. Okay, and that's always going to be the time for the S wave minus the time for the P wave. Okay, so lag time is always going to be the time for the S wave minus the time for the P wave. Okay, then you have the epicenter distance. Right? I said to you guys are all seismologists, you're at the seismic station. You know that you saw that a P and an S wave came up, and you need to figure out where around you is the epicenter. Okay? So the epicenter distance is how far you are from the epicenter. That's something you're going to have to determine, is how far are you from the epicenter of the earthquake in general. Okay? And finally,
Distance is how far you are from the epicenter of the earthquake. And epicenter location is exactly where the earthquake started, the exact geographic location or region.
okay, so epicenter location is the location of the epicenter, the geographic location. Okay? All of this you are going to have to know how to determine. And we're going to take it slow. All right? We are not going to finish this lesson today. We're going to start actually using your reference table today. And then tomorrow, we'll continue it and do practice. Okay? All right, so everybody have our science reference table, page 11. Okay? For tomorrow, especially people who are home, make sure you have a scrap piece of paper that has a straight edge. So you don't want to rip it out of your notebooks, okay, and then have a jagged edge. You want a straight edge. Okay, so for tomorrow, you're going to need that.
And once you have those down, you can use your chart to help manipulate questions. So the first thing you need to understand are your axes. The vertical axis is your travel time, that's in minutes, goes from 0 to 24 minutes. Each line is an increase of 20 seconds. Your horizontal axis is your epicenter distance. That goes from 0 to 10,000 kilometers. Each line increases by 200 kilometers.
Okay, this is the first graph where time is not on the x-axis. Okay, this is the first graph that I have shown you where time is not on the x-axis. So be careful about that. The other thing is, down here, look at your graph. You see where it says epicenter distance? And then it says parentheses times 10 to the third, right? That's called scientific notation. What scientists did is they take really long numbers that you're more than likely going to, mess up by forgetting a zero or adding a zero, and they put it into scientific notation for you, okay? If your answer is 1 times 10 to the third, okay? So if your answer down here is 1, it's not just 1. It's 1 times 10 to the third. To take that out of scientific notation, since this exponent is a positive 3, you move the decimal place, right? Because technically this is 1.0 times 10 to the third, right? You move the decimal place 3 times to the right. 1, let's do this way. 1, 2, 3. So technically, this is the same thing as saying 1,000. Okay? 1 times 10 to the third is the same thing as saying 1,000. But if you got your answer just by looking at the chart as 1, and you don't put times 10 to the third with it for the 1,000, you're wrong. So be careful with that. Okay? Be very, very careful with that. Okay. Let's continue.
Very important to keep your P wave and S wave curve straight. Notice that the closer together they are, the smaller the lag time. The farther apart they get, the bigger the lag time.
So in between the two is the lag time. In between the two graphs, that's the lag time. So when they have a small distance to cover, right, the lag time is very small, and it should make sense because the P wave is way faster than the S wave. So the further the distance you have to travel, the P wave is going to be there that much faster, and therefore the lag time is going to be that much more. Okay?
Farther away those waves are going to be from the epicenter. So what happens here is you have to understand that P waves travel faster than S waves. So the faster the P wave travels, and the farther it's going to travel, the bigger the gap you're going to get between P wave arrival and S wave arrival. So here's just a couple examples on how to use this chart. What I like to do is I like to tell all my kids to identify keywords like travel time, arrival time, origin time, and try to figure out what is given to you that you can get directly off the chart.
Okay, so let's write this down in our notes so that we can, when you guys study, you have a clue as to how we got the answer. Okay? S-wave travel time is 4 minutes. How far does it travel in this time? This is just a very simple question on how to read this chart. You can't get any simpler than this. Because it's just reading the chart. You don't need to figure anything out, right? You want to write out a given list. Or you want to say to yourself, what is given to me? Can I infer anything from it? And what am I looking for? Okay? So in this question, what is given to me? What's given to me? Travel time is what? 4 minutes. What else is given to me? The kind of wave. That's very important. Because if you mess up what kind of wave it is, then you're looking at a completely different answer. Right? Is there anything else that's given to me?
You know, to look for how far it travels.
Exactly. You're looking for the distance. Okay, so when you write out your given list, you're going to want all three of those.
S-wave travel time is 4 minutes. How far does it travel in this time? So your keyword there is going to be your travel time. Okay, so they actually give you a 4-minute travel time. So you find your travel time of 4 minutes. We want to know how far did travel in that time. So you follow it over to your S-wave, follow it down. Turns out to be about 1,000 kilometers.
Right, 1 times 10 to the third or 1,000
So those
kilometers.
are some of your basic problems like that. Make sure you know that.
That's super basic.
How long does it take a P-wave to travel 5,000 kilometers?
Okay, so how long does it take a P wave to travel 5,000 kilometers? All right, Ethan, give me one thing that you're given out of this question. The type of wave that it is, which is P wave. Okay, that you're traveling 5,000 kilometers. Now, Marco, what am I looking for? What variable?
How long it takes
Right,
to travel.
exactly. So how long is also known as the, starts with a T? Time, right? So you're given that it's a P wave. You know that it needs to travel 5,000 kilometers, and you want to know how long. So this is simple. You go over to 5, because that's 5,000, right? You go up, and you want to make sure you're at the correct wave. Okay? You're up at the correct wave, and then you go over. And you notice that this is a little bit higher than 8. It's not on the 8 exactly. So this isn't gonna be 8 minutes only. Right? How much is each one of those lines worth? Did you guys remember what he said? 2? 20 seconds, exactly. So the answer should be exactly 8 minutes and 20 seconds. So guys, tomorrow we are going to start here. All right. Make sure that you have your reference table printed out.
If it was broken up by 3, wouldn't it make more sense if they made it like 5:33 seconds instead?
Yeah, but it's 33.333333 seconds then. So 20 seconds is a nice even number. Yeah, that's why they do that. Yeah, and there's 60 seconds in a minute. It's okay. You know what?